extra strong
Roman concrete,
fully hydraulic
structural
Welded connections.
It's the
structural engineering
podcast.
Hey, welcome to this week's episode of the Structural Engineering Podcast. My name is Max,
And I'm Zach.
and this week we're talking about load path, the most important thing.
At least to structural engineering.
Yeah, I think
But you'll find probably more than just structural engineering. Stay
I don't know.
tuned. Stay tuned.
But before we talk about that, let's talk about the news. You got any good news for us?
You know, this week I found something that popped up that was super, super cool. And I thought, instead of the news, which I don't enjoy waking up to the news every day, so maybe we mix it up a little bit. I want to talk about a little bit of a case study that just came out in the Structure magazine.
Whoa.
And let me read the title to you, and I know you're going to love this. Residential seismic design using viscous dampers.
Oh, yes.
Man, and what I think is awesome is when we interviewed with Taylor on the podcast, they brought up that they're using them in residential construction.
Yeah,
And
he
then,
kind of
you know-
pushed it out. It was just like, yeah, you can use them in a house.
And then like 2 months later, 3 months later, boom, there's an article with a case study about this. So
Man, this is Structure Mag?
yeah. So, and it's in the July.
Can anyone get Structure Magazine? You don't have to sign up for that, or you have to sign up, but you don't have to pay.
Yeah, you can get it online.
That's it.
Yeah, exactly.
Yeah.
You don't have to pay. It's
Yeah.
it's in the July edition of Structure magazine. Yeah, so it discusses why they used them, and to step back a little bit, it goes through light framed residential construction has historically performed really well in seismic events.
Yeah,
in all
R6,
ranges, high seismic,
snaps.
everything. It's super redundant. There's low mass. And here's something I think is really cool that we never really consider or think about, but there's applied damping resulting from damages of finishes. So the structure is damping by the finishes. But what it's saying is happening is that in these high-end residential construction, instead of choosing finishes that are not, light construction or light finishes,
Yeah.
and finishes that will crumble or be able to
They're too
see-
nice, too strong.
Yeah, exactly. They can't see large inelastic deformations. So this engineer decided to, with all that information, he went to the owner of the building, discussed with the owner of the building what they want to do. I'm guessing this high-end owner of this house wanted a building that could probably survive an earthquake.
Yeah.
I think that's a pretty hot topic, especially in California, which is where this building's located. So they wanted the engineer to come up with a system for the maximum considered earthquake that would result in very low financial losses of the structure and really not have much issue. That meaning the finishes aren't breaking or falling off, and they came up with using Taylor devices, dampers through the structure to prevent that from happening. Just like if you could imagine, any high-end structure has a lot of glass, cantilevers, probably very difficult to get a shear wall in there. So they used braced
Is it
frames.
not sure? It is brace frame, really.
So they used the braced frame direction with the Taylor devices damper. They used the viscous dampers to be able to dissipate the energy of the seismic event. And if you go listen to our Taylor devices, you'll learn that is dissipated by forcing a fluid through an orifice during the deflection. And you have to go listen to our podcast to learn more about their stuff.
Definitely.
But
I just pulled up this article and I'm flipping through it a little bit. I like that it was only a 5% increase in total construction cost, which in a big building, could be a large number, but 5% is pretty small. Especially if you're talking a house in a seismic zone that you'd like to not repair in 50 years, whenever an event may occur. Like you're good. It also mentions that damage tends to occur beyond a 1% drift limit. So finish damage, and that is the limit that they kept this building at. And I wonder, that's pretty small. We're looking at a steel concentric brace or whatever this brace is. Our amplification factor is like a 5. Is that right? So I don't know, 20-foot walls. That's what's that, 1 inch?
So looking at this article and the system they chose and whatnot, what does that make you think the future of design is going to be based off of?
As far as a system?
Performance-based design.
I think this lends very well to performance-based design. Don't you?
Absolutely. I really think in 10, 15 years, the whole industry pushes to a performance base of design for seismic, maybe a little longer, and then it will be wind.
Yep. I mean, 5% increase in cost, that's nothing, especially for a high-end home. Your finishes are the most expensive thing here. So
Now, something I'm curious is, now most house designers are just using wood shear walls. It's going to take a pretty specialized engineer in the current time to design a system like this.
Yeah, I think it's probably a pretty specialized engineer doing these high-end homes. They've got a model of the lateral analysis. I'm not even quite sure what software this is. It almost looks like a RISA.
SAP 2000 nonlinear analysis.
Oh.
It says it right to the left of the picture.
Well, I just look at pictures. Yeah, I mean, I think a lot of engineers have this capacity. Maybe not your standard residential engineer. Nothing wrong with that. But it takes a little extra work. I bet the design fee was 50% to 100% more than what it would have been for just a standard house. I'd like to guess, but that contributes so little to the total cost. I wonder if we can talk to this structural engineer just briefly at some point. Get a snippet of the design process of this house. That would be really cool. Just a quick phone call.
Let's do it. Let's reach out. How about now we go and talk about a little load path?
Oh, that could be fun.
Now that we're 11 minutes into Is there anything else you want to talk about this house at this point?
No. Other than it looks very nice.
Okay. So Max, let's dive into a little load path now, our topic for this episode. And what do you think about load path? How does load path affected your life?
It's everything to me. As I said in the beginning, is the most important thing, and I meant it. As far as structural engineering goes, it is the golden rule. Most
engineering failures is due to load path, insufficient load path.
That's right.
So there, it is the most important thing.
Yeah, absolutely. I found some good examples of failures. One was the bridge collapse. What was that? Was that a Hyatt Regency?
Right, where the detailing of the bridge, the walkway was changed during detailing, steel detailing, and changed the load path of the structure, and it failed, and unfortunately people lost their lives.
Yeah. So that's, I think, a very good public example. But like you said, it's AISC says the most common, and we'll link this in the show notes when we get there. But AISC has a really good video. I can't think of who the presenter is, talking about load path, both gravity and lateral, and especially connections. The presenter is a connections designer, and is so good.
So let's take a step back. What is load path?
It is the way that your load moves through the building. But that's not a very good definition. I don't know. Do you have a good formal one?
Load path is simply
Load path is simply the direction in which each consecutive load will pass through connecting members. The sequence commences at the highest point of the structure, working all the way down to the footing system, ultimately transferring the total load of the structure to the foundation.
That's a well thought out answer, I think.
Which also explains why most engineers often design from the uppermost members first and progressively work their way down the structure following the load path.
Absolutely. So you may remember from our seismic podcast, we talked about Loma Prieta, where the buildings came apart in the members that they were designed. The wall came off of the roof and the floor, and everything just separated. That right there is is why load path is so critical, and exactly where it tends to fail the most. You need to be able to, especially as a young engineer, trace each load through your building, and gravity tends to be the easiest, and then lateral is a little more complicated. But literally pretending you are a little piece of load, a little load man, and you hit the side of the building and you walk your way through, like, that's the way. What are you laughing about?
That's perfect. I think the rest of the podcast we're going to use the little load man.
Be the load man.
The load man hits the building and he's trying to work his way to the foundation.
Yeah.
And I think we just lost half of our listeners.
No, this podcast partly came around. We've been wanting to do Load Path 1 for a while, but someone Someone on Instagram asked if we could do something about tiny homes, which I'm into. I've got a tiny camper myself. But designing a tiny home and a mega home and a warehouse and a skyrise all have the same thing in common that is critically important, and that is load path. No matter what, you can kind of break everything down to a roof, transferring to a cord, if you're looking at lateral, transferring to a shear wall, and all the connections in between, down, So there's this sequence of connections that has to occur no matter what the building is. So I think, whether you're building a tiny home or a mega home, if you can follow that sequence in your head and make sure there's a connection the whole way down, you are good to go, regardless of the size.
That was something I was told really early on in my engineering career. As long as there's a load path, you won't have failure.
Yep, absolutely.
Now that has limitations. There's no doubt. At a certain point, like you brought up the failure of the walkway. Sure, there was load path. It failed.
Yeah, it just changed.
Exactly. So in general, if you have a load path and it is sufficiently designed, your structure works. That's it. I think as well, that's what most people reviewing drawings are looking for. That's what your higher ups were going to look for when you get to detail your first project, because to me, the big load path chunks, you got to have your post and beam and your foundation. You got to have your roof, bearing walls or whatnot, bringing down. That's fairly straightforward. The connections of those is where it gets a little more complicated, and that's where you kind of have to dive a little bit more into the code for those elements. But then, when you get into a lateral load scenario and have to track that lateral load down your structure, I think that's where a lot of engineers get, pretty stuck on.
Oh, yeah.
And then also to that point, and this is something someone on the Instagram brought up too when we discussed a little load path on there, is a lot of young engineers get really confused when there's more than one load path. What do I do? Why am I doing it? And this kind of goes back to a lot of good comments that a lot of professionals that we've interviewed has said is go ask too many questions. Learn as much as you can. So when you get to that point with too many different load paths, go ask the question, what's the best load path? What I was told is just a good rule of thumb is the shortest load path is always the best load path. If it can go through 2 nails rather than 10 nails, you have a better load path if it's shorter. So that's probably the best place to start. But to always ask, go ask the question. You're going to look good if you're trying to ask a question on load path. Hey, I've got this lateral load in this shear wall. I've got all this floor framing, and then I got another shear wall. How do I transfer the shear from one to the next? And they're going to go, oh my gosh, this guy's really thinking through, or gal, is really thinking through the system, how this all goes together. And I think that's something, super confusing once you start trying to detail things, because when you engineer it and you're like, okay, that's a shear wall on top of a shear wall, they're additive, and you just keep working your way down. But when you start getting to the details and specifying connections, that's where it really starts to really matter.
Oh yeah, it's definitely something that is a bulk of it is in the details. The design side is substantially more in those larger elements. What do you say we walk through a typical structure, maybe wood, and do a gravity path and a lateral path, and really, what is this thing? What do you expect to see in these elements?
Yeah, so I think the best example is just a one-story house, right? Everyone's seen a one-story house. It's got a gabled roof, bearing walls.
How about a one-story tiny house? Can we do that instead?
Absolutely.
Okay.
There's nothing different. It's got a roof, and it's got walls, and it's got a foundation. The foundation maybe goes to wheels for your instance, but you have some sort of element framing your roof horizontally supporting the roof loading, which your dead, live, snow, wind. That roof load then transfers over to your bearing walls, which is usually a 2x4, 2x6 stud wall. Some scenarios that could be a beam of some sort with, for a header or whatnot. Those elements will have their own studs attached to them, but now you're into your walls. That load comes from your roof down to your walls. Those walls need to be able to transfer that load down, so your studs have to be adequate for that loading. And then from your studs, it goes to your foundation, and you have to make sure that your foundation is adequate for that vertical load. The other thing within all of that is your vertical load is not always necessarily in the direction of gravity either. you will always have a dead load or and a live load, but you also will have a wind pressure, which can be in
I
suction.
was going to walk that one, actually, if you don't mind me taking a walk here.
Take it for a walk, Max.
Let's roll. So going the other way and stealing this from you is our wind uplift on a structure. I like this for tiny homes because you have to move them. I know about this because one of my roof panels came off. So
load path, Max, load path.
I know. Okay, so
live and learn.
Looking at negative pressure on a roof, you've got a roof panel. Let's say you have a metal panel, and then that metal panel is nailed down to some sheathing below. So you have from uplift of the metal panel all through nails. Nails are not good in tension. Those should all be screws, right? And then screws go down to the plywood. The plywood goes down to the studs. The studs, again, should probably be screws when it comes down to uplift. Sort of talking tiny home, but I'm talking any home. Nails just aren't awesome in withdrawal. You can get ring shank. Anyway, each nail in the stud extends out to the edge, and then those studs are either sitting on top of a double top plate, however they're attached there. Generally, they wouldn't have very much uplift capacity as you would sort of picture the detail, and that's where clips come in. Hilti, or rather Simpson, in my tech, they have every clip in the world. You just attach that joist down to the stud, and now you've got a tension, and then you work that way down. You've got to keep that tension the whole way down. Tension goes into the stud, through the nails, through the clip, through the next nails, stud, down we go. And however you attach it to the frame, the foundation, you need to keep that tension capacity going. So either another clip, a strap, whatever it is, fully nailed top to bottom.
And we've got a FEMA tech guide on high wind regions for that exact thing that we'll also supply in the show notes for you, nice. As well as on our website that goes through that exact load path that Max discussed. Something I kind of just want to jump in, and it just came to my mind.
Yeah,
is what you just said about withdrawal or tension loading or shear loading, and that's something else I've always learned. Shear is the best load path always. Now, yes, you have to resolve loads and tension. It's going to happen. There's no way to get out of it always. But if you can, with your load path, resolve as much as you can with shear, it's a way better load path.
Yeah, the only gripe on shear is it tends to be a more brittle failure. So if you're looking at something that you want some ductility in, shear is not usually the answer. But for everything else, absolutely, yes.
Yes.
Should we do a lateral system and kind of walk it the same way?
Yeah. Now that we've gone through the gravity, let's chat a little lateral. So what kind of load do I got, Max, for my lateral
system? Let's be a little wind load man.
So I've got my tiny house, my normal house, any structure in the world. I've got a wind load on it now. So that wind pressure is going to push horizontally to my building. So it's going to push on my walls, it's going to push on my roof, and it's also going to suck on the walls and suck on the roof.
Wow.
Depending on what type of wind loading you do, which listen to our wind podcast 1 and part 2 to learn about all the wind loading that you could ever imagine. They have different pressures, etc. But anyways, on our building, we've got pressure pushing on it. That's going to go, when you push on the wall, it's 1-story wall, half of it's going to go up to the roof and half of it's going to go down to the foundation. The half that goes up to the roof needs to be transferred through the roof diaphragm to your resisting elements that are parallel to the direction of the loading. So now the roof diaphragm has this loading in it. I have to get it over to the shear walls for like a trussed roof that is you're then blocking from the roof diaphragm between the trusses to the top plate of the 2x4 wall or 2x6 wall. That wall is then sheathed with plywood. That wall could be sheathed with really anything, gyp, plywood, OSB, plywood's better. And then that wall is going to take that loading, transfer it down to your foundation. But when you are looking at these individual elements, they're going to have different pieces you need to design for. Like your roof has a cord element. So when that thing goes into bending, you have a tension cord and a compression cord that you need to resolve. Now, when you get to your shear wall, you have the same thing. You have this overturning force of your cord elements. So that's where you have these hold downs that will be in tension to resolve that force. You can definitely is something that's required by code. What I like to always hear from young engineers is, when was the last time you saw a house tip over? And that's not necessarily what you're trying to do. I would love for someone to show us an example of when a diaphragm cord failed and that was catastrophic to the structure. We're not necessarily trying to, we're resolving the load, right? Every methodology has a different way to resolve these loads, how to go through them. when we're designing these diaphragms with, we have a moment in them because it's a simple diaphragm is a beam, really. It's got a reaction point on each end. It's a distributed load on it.
I like to think of it as a TJI.
TJI, there you go. Sure. TJI.
Yeah, well, because it's got the plywood or OSB in the middle, and then the top and bottom cord, are your double top plate. It's like a giant TJI. Sorry.
Big TJI.
I ruined your train.
Yeah, I totally.
Derailed.
So while you're tracking your load path, you got to make sure you're resolving all your forces while you go through the load path. And I think the best example is what we just went through with the cord. You have this force in there that needs to be resolved. So the fact of this tiny home or a house or anything, let's say out of wood, your cord is majority of the time, if not always, going to be your double top plate of your wall, but you have to make sure there's load path to make that your cord as well. So in a wood building, there's a lot of blocking between the roof sheathing or diaphragm down to the double top plate of your wall to allow all these transfers of loads and etc. So anyways, your load is, you go through your shear wall, you've got your overturning, and then you resolve those forces into the foundation, and then the foundation, you have to make sure it can resolve the forces into the soil. And then there's your lateral load.
That's it. I looked up, I have a digital copy of one of the ASCEs, but I only have half of the digital copy. And I looked up load path because I was curious how many times it was mentioned. And I only go up to seismic, so I'm sure it's mentioned in wind a couple times. But you only get it 12 times. But it's in there, and it's super important. And there's something in the very beginning, chapter 1, and they're talking about general structural integrity. 1.4.1 in all of the ASCEs is all the same, and it's load path connections. It goes a little deeper to say it must resist 5% of the portion's weight.
Right, by inspection.
By inspection, you say, it's fine. Keep in mind when you're thinking of load path that you should always have that 5% in there, and I think that covers a lot of load path in general, like a redundancy. That was really rambly. Let's try that again. So there's actually a minimum connection strength that's required in a load path. We've got one for lateral forces sort of globally, and this is 10% of the building weight. But then we also have one for load path connections. That's all parts of the structure between separation joints shall be connected to form a continuous path to the lateral force resisting system. In addition, any smaller portion of the structure shall be tied to the remainder of the structure with elements having the strength to resist a force of not less than 5% of the portion's weight. The thing is, the second part rarely comes into play because we're often holding the structure at a minimum, which would be 100% of the portion's weight. But it's good to remember if you've got some component that is in some way supported on its own, you still need to resist 5% of the structure's weight.
So that was something also that came up quite a bit while researching, load path and his redundancy.
Yeah.
And something, kind of talked about too at the beginning of the show with that house using viscous dampers. They say, wood building is very redundant. And I think there's some truth to that, where I found that this redundancy idea kept coming up, and maybe this is kind of coming off the topic of load path, but it also ties with load path and the whole question of having more than one load path in general. But where it kept coming up a lot was bridges. Bridges should have inherent redundancy.
Absolutely.
So we're not here to talk about bridges today.
Yeah.
But that's something, to also think about when you're designing something. Is this a redundant system? And the code does a lot to make sure that if you don't have a redundant system, that your elements for specifically for lateral are super stiff and super strong to be able to take those loads. So
let's talk about a couple things that are either often missed or important here. I want to talk about different roof heights. This is, I think, a common miss and a common architectural feature as well, is when you have a high roof in the center maybe, and then a low roof around the perimeter, or maybe you have two different steps at different angles, and that looks so cool.
One might call that discontinuous.
Oh, okay. So maybe you would call it discontinuous, and you'd have different steps. And as your diaphragm bends here, you don't have a continuous diaphragm anymore. So you have to break these up into two sections. and it'd be really nice if you had shear walls in the middle of them. You probably do, but what I wanted to say on this is that you need to transfer that end force from a high section to a low section where they come up and touch each other. If you just have a wall that goes high and you don't think about it at all, and you put your sheathing on the top and the other one comes in on a ledger, you're going to get an accidental transfer of shear force, and you might not ever know that you made a huge mistake until we get a design wind event. You need to consider those forces down through that upper shear wall, whether that be a wood shear wall, or if you're designing out of steel, you need to brace that thing so that the force can transfer down through the diaphragm, down to the lower diaphragm, and either dump into the lower diaphragm, or what would be much, much better is go right down to a shear wall. That's a big miss, and that took me a while. I think early on is something I kind of forgot a couple times is I don't know, not do it. What's the other one? Stiffness. Tell me about stiffness.
Stiffness is really the whole key of this whole game we're talking about with load path.
Load path is the key of the game of structural engineering, and stiffness is the key of the game of load path.
Completely. Load is going to track to the stiffest element that is there. And so, again, that's going to be your best load path. If you think about an infinitely stiff beam, and the reactions are springs, we have 4 reactions points that are spring elements.
I remember this homework problem.
And each spring has a different stiffness. And you have a distributed load on this beam. The spring that's going to attract the most load is the stiffest point. Or this has the stiffest spring constant, right?
That's right. They all deflect the same amount, and your high spring constant will result in a way higher resistance force.
So to me, in my head, that's the most simplest way to discuss stiffness. A simple beam and some springs. They all will deflect, and the stiffest spring will take the most load of your system. And easy example is again, let's say wood building with a rigid diaphragm. Let's say you have an 1.125" plywood. That can be treated as a rigid diaphragm. Based off of your shear walls, how long they are, the nailing pattern, all that kind of stuff. You can figure out the stiffness of your wood shear walls based off there. The NDS has a 3-part and a 4-part equation for determining deflection of a shear wall. Figure out how much it deflects. Let's say from 1 kip. Your stiffness is kips per inch. Sorry. Mm-hmm. So you take your kips that you applied on that shear wall divided by the deflection of that shear wall, and there's your stiffness. There's your spring constant for the diaphragm. You do that for all your shear wall lines. You take your distributed load on your diaphragm or the force on your diaphragm, and right there you have a rigid beam with different springs, and then you can distribute based off of stiffness of your elements.
Yeah, and a fun way you could test this, it's sort of makes sense, but if you're having trouble picturing it, if you've got EnterCalc on your computer, you can make a beam analysis, and you could change the moment of inertia of your beam and watch. So do a continuous load over several supports and watch that even out as you move along. I got another one for you that I see all the time, and that is accidental load transfer. Let's say you've got a warehouse and you've got long span trusses in there, and you put up a CMU wall because you need to box in something. You got to put in a bathroom in the middle. So you run your CMU walls all the way up to the top, and they're just sitting right at the bottom, or they're clipped into the joists or something. Those are now going to take load, and that probably wasn't intended.
There's a great case study, real world event that happened. I don't know if this is what you're trying to reference at all, but during the Northridge earthquake, there was at a hospital an area where they stored all the ambulances, and it was made out of a kind of a lean idea, metal building with all open walls, except it had a roof on it. They didn't like how much, I believe, rain and wind came in, so they put masonry. They infilled between all the frames with masonry. Northridge happens. You have these heavy walls, this very flexible building, as you know, metal buildings are insanely and very inherently flexible. It deflected as it's expected, and the walls did not move with it. It took out the walls and blocked and destroyed all the ambulances at this hospital.
Yeah, that's a good example. That's definitely what I was referring to. Mm-hmm.
You're a genius.
That's exactly it. I don't know. Maybe a simpler is like, you have a house, you've got your floor joists, and you nail a little post in your kitchen. You want to have, some post decorative, and you nail it to the bottom of a floor joist. Now that thing is taking twice as much, if you put in the center, twice as much load as the walls are, and it's just going to buckle immediately. It's collecting way more load than it was ever intended. So all these places where you don't actually want to be collecting load, you need to think about the detailing and put slip connections or whatever it's going to take to make sure that those things aren't collecting load.
So in summary, be thoughtful in how you design and track where your loading is going based off the stiffness of your elements.
That's my exit.
Thank you for joining us this week. If you have any questions on our podcast in general, you have any corrections, questions, anything you've got pertaining to any of our episodes, obviously specifically for this podcast, ask us any load path questions. You can ask us, maybe a question you're trying to work through in your day-to-day life as an engineer. Maybe you're trying to figure out some load path and you'd like some help. Please reach out to us. Max is an expert in load path. I can figure out what's going on. Please reach out to us. We'd love to hear from you guys. We continually are getting lots of questions, so keep them rolling. We're loving it. We have a couple more podcasts coming up with some industry experts that you guys are really going to like.
Oh, I'm out. You said it all.
Oh, geez. Catch you next time.
See ya.